So we have three talks this morning. First talk, happy to welcome Priyanka Majumder from ISI Bangalore to speak about Arakelov self-intersection numbers on modular curves.
Thank you for the introduction. So I would like to thank the organizers for giving me this opportunity to speak here. So I'll be talking about Arakelov self-intersection number or modular curves. So this is I'll present two results here. One is with my supervisor Anna von Pipish, and another is work with Debargo Banerjee and Chitravana Choudhury. Okay, this is the outline of my talk. First, I'll give the introduction, then some preliminaries, and then the main results. So let n be any positive integer and gamma be a subgroup of PSL to Z of this gamma is called the congruent subgroup of level n. And by x gamma, I denote the modular curve associated to this congruent subgroup gamma over some number field k. So one example of level n congruent subgroup is this group gamma naught of n, and the other examples are you can take gamma 1 n. This is defined as ABCD belongs to PSL to Z such that this is congruent to 1, 0, 1 mod n. One more example is gamma n. ABCD belongs to PSL to Z such that this matrix ABCD is congruent to identity matrix 1001 mod n. So this one is called the principal congruent subgroup. So congruent subgroup of level n is any group gamma, any subgroup of PSL to Z which contains the principal congruent subgroup. These are called the congruent subgroup of level n. So here I'll be talking about the modular curve associated to this particular congruent subgroup. So which I denote the modular curve by x naught of n, and my number field is set of rational number. So now I define the Arakelov self-intersection number on that particular modular curve. So let G gamma be the genus of this modular curve x naught of n. So there is a formula for genus. For any congruence group gamma, the genus equal to 1 plus dn by 12 is 1 minus epsilon 2 n by 4 minus epsilon 3 n by 3 minus epsilon infinity n by 4. So this is d is the degree of the map x1 to x gamma, and this epsilon n is order 2 elliptic fixed point, and epsilon 3 is order 3 elliptic fixed point. Number of elliptic fixed point of order 3, and epsilon infinity is the number of cusp. So this way you can exactly compute the genus of this, and for this particular group a gamma naught of n, you can use this formula and you can get the genus of gamma naught of n. Now for genus greater than 1, there exists minimal regular model which I denote by curly x naught n over Z for the modular curve x naught of n over Q. So what do we mean by the minimal regular model? Means it's an arithmetic surface over spec Z. That is, it is a scheme of dimension 2 with a proper flat morphism. F goes from curly x naught n to spec Z. So one can draw this following picture. So suppose this is your arithmetic surface and this is your spec Z, and there's a map from here to here. So any element here, there's a fiber over P. Suppose this looks like this, two vertical divisors, and we can compactify this system by adding a point infinity, and over infinity we have the special fiber is Riemann surface. This Riemann surface we denote x naught of m C. So suppose we have two horizontal divisor in the arithmetic surface, we say that these two divisors intersect at infinity. So now, in 1974, Arakelov introduced the intersection theory on this such arithmetic surfaces. So now let omega x naught n be the relative dualizing sheaf on this curly x naught n. The Arakelov defined a metric on that omega x naught n, and Arakelov self-intersection number is given by this omega square. This is exactly equal to omega bar. Omega bar is this pair omega and the Arakelov metric. And this quantity is we call Arakelov self-intersection number for the relative dualizing sheaf on curly x naught of n. And this is a very important invariant in Arakelov theory. So how do you compute the Arakelov self-intersection number? Arakelov self-intersection number of the dualizing sheaf can be written as two parts. First part is encodes the finite intersection of divisor coming from the cusp 0 and infinity, and the next part is the analytic part, which is given in terms of canonical Green's function, or sometimes people call the this Green's function as Arakelov Green's function. So this omega square x naught of n, this is independent of the number field k. If the minimal regular model x naught of n, this is semi-stable over ring of integer OK. Okay, now I recall some preliminaries. First of all, there is a hyperbolic metric and a Laplacian on the x naught n, which is denoted by mu hype z. It's a 1-1 form corresponding to the hyperbolic metric, and locally it is given by this. And one can compute the volume, hyperbolic volume of the group. So by hyperbolic volume, I mean the V gamma. This is exactly equal to x of gamma for any congruence group. You integrate mu hype z. This is exactly equal to the fundamental domain. You integrate upon the fundamental domain of gamma, mu hype z. This is exactly equal to volume of PSL to z, which is pi by 3, and the index gamma 1 gamma. So this is always finite for the congruent subgroup. So we are interested in such subgroups where the volume is finite. Hyperbolic volume is finite. Okay, so on this x gamma, we have the hyperbolic Laplacian, which I denote by del hype. And locally it is given by this y square minus y square into dou square dou x square plus rho square dou y square. So for if you take any smooth function f on x gamma, and if you apply this hyperbolic Laplacian and multiply with this hyperbolic 1-1 form, we'll get 4 pi d dc f, where d and dc are the two differential operator, dou plus dou bar, dou minus dou bar by 4 pi I. Okay, now I introduce the canonical metric and the canonical Green's function. So what is the canonical metric? 1-1 form corresponding to the canonical metric is I will denote it by mu can z. This is given by this quantity here f j z. This f1 f2 until fg it denotes the orthonormal basis of weight to cusp forms with respect to Peterson inner product. So Peterson inner product is fg Peterson inner product. This is equal to x gamma fz is z bar mu hype imaginary part of z square mu hype z. So this is the Peterson inner product with respect to this metric. This is the orthonormal basis. These are the orthonormal basis f1 all fj's, and using this we can we are defining this canonical 1-1 form, and if you calculate this volume with respect to this mu can, you will see this volume is 1. Okay, now let g can be the canonical Green's function on x gamma. This x gamma, this g can is characterized by the differential equation DDC, G can ZW. This delta is a Dirac delta distribution. This is equal to this canonical 1-1 form, and this is satisfies this normalization condition. If you integrate with respect to canonical metric, you'll get 0. So similarly, for any smooth metric, you can define the Green's function. So if you take any smooth metric on mu, the Green's function is defined like this. G mu ZW plus delta WZ. This is equal to mu Z by volume of X with respect to mu. So here volume is 1, that's why it is only mu con. And with this normalization condition, if you integrate this Green's function, G mu ZW mu Z will get 0. So here here I have taken mu as mu con, or you can also take mu hype, which I have defined in my previous slide. So now one of my result is regarding this canonical Green's function. This is the first theorem. So I say that if n be any positive integer, and we have taken that a gamma as a congruent subgroup gamma naught of n, then 2g, here g gamma is the genus of this group gamma naught of n, 2g 1 minus g gamma, g can 0 infinity, is equal to 2g log n plus little g log n as n goes to infinity. So this is from my PhD work, and main idea is to how do we prove this? We prove this. So there is if you take two Green's function, if you take the difference of two Green's function, G hype ZW minus G tan ZW, this is exactly equal to phi Z plus phi W, where phi Z equal to integration over x gamma G hype ZW mu con zeta minus half of integral x gamma cos x gamma. So G hype ZW, not ZW, zeta eta mu con zeta mu con eta. So this is the starting point. This identity is due to Jorgensen and Kramer. So now this if you hyperbolic Green's function are quite well known from the literature, and now we calculate this integral, and from there we calculate this asymptotic formula. So why we are interested in this asymptotic formula? Because our motivation to prove this theorem is this, because analytic part is exactly equal to this left hand side, analytic part of the self-intersection number of the dualizing sheaf. So in 1997, 1998, Abbe Sulmo and Michel Ulmo, these are the two papers, they proved this same asymptotic formula for any square free n. And following their line of proofs, in 2020, Banerjee, Bora and Choudhury, they proved that for n equal to any prime square, this asymptotic formula holds. But however, our proof is different than their proofs. Okay. So using this theorem, now I will give my second result, which is this. This is joint work with Debargo Banerjee and Chitrabhanu Choudhury. So I take any prime p and gamma as gamma naught of p power r. Then the Arakelov self-intersection number of the dualizing sheaf of curly x naught p power r satisfies this asymptotic formula. So here curly x naught p power r is a minimal regular model for this modular curve x naught p power r over q. So for simplicity, we take r is equal to 3 and 4. So this main idea comes from the paper of Eric Sobin in 1990. So in this paper, he has given the explicit description of the regular model for modular curve x naught of n. So the special fiber of the regular model for x naught p power r over fp, this depends on the parity of p mod 12. These parities are p congruent to 1 mod 12, P congruent to 5 mod 12, 7 mod 12, and 11 mod 12. Okay, so a special fiber, these are some pictures from this paper of Vedic Sovel. The special fiber of the regular model of x naught of p power r. So for r equal to 3, the special fiber looks like this. This first picture is for p congruent to 1 mod 12, second is for 5 mod 12, third 7 mod 12, and 11 mod 12. And for r equal to 4, the special fibers looks like this. Again, the parity is from 1 mod 12, 5 mod 12, and last one is 11 mod 12. So for each cases, we had to calculate the intersection of these divisors, and then we can conclude our second result. So some rough outline. So by using faulting-Rayleigh theorem, one can show that this Arakelov self-intersection number of dualizing sheaf is exactly equal to this part, analytic part, and this geometric part, and geometric part is exactly equal to this 1 by g gamma minus 1, g gamma v naught v infinity. This is the Arakelov intersection product. And v naught square plus v infinity square by 2 and plus h, and this h is equal to big O of log p. So here Vm means V0 and V infinity. These are the linear combination of the all irreducible component of the special fiber of the minimal regular model, which I have showed earlier in the picture. So Vm are basically the all linear combination of those components. So we have explicitly computed V naught and V infinity for each of each cases, and then computed this thing. And finally, we got as p goes to infinity, this part is equal to g log p power r plus little g log p as p goes to infinity. So like my theorem 1 says this part is 2g log p, 2g log n plus little g log n, and my geometric was is 1g log n. So together we get the asymptotic formula for the Arakelov self-intersection number of dualizing sheaf, which is 3g log n plus little g log n as n goes to infinity. So these are two references. First one is with my PhD supervisor, and second one is Devargo and Chitravanu. So from these two papers, you'll find the detailed proof of theorem 1 and theorem 2. Thank you for your attention.